Welcome to week 10 and lecture 9, which is going to be on examples of combinatorial circuits. During this week, we're going to talk about the exclusive OR otherwise known as XOR gate, and its common applications, some of which include encryption, parity generator, and checker. And of course, we're going to talk about adders and subtractors. So let's define XOR. XOR is defined after this truth table over here. Now, the message you need to keep is that the output of the XOR function is 0 if both inputs have the same value. So if you pass 0, 0 for x and y, the output will be 0. Likewise, if you pass as inputs 1 and 1, the output will be 0. So essentially you want only one of the two inputs being equal to 1 and the other one being equal to 0. This is the Carnot table that comes after this. And as you already know how to use Carnot tables, this is the minimized function of the exclusive OR. Obviously, after the Carnot table over here, you see that x XOR y equals x dash and y, or x and y dash. What comes naturally after that is the identities which are here. Now they are quite obvious. X XOR 0 gives you x. X XOR 1 gives you x dash. So pretty much these two summarize how I described to you the truth table. Then you got x XOR itself giving you 0, of course, because as we said, this is what happens here and here in the first and the last row of the truth table. And that defines the exclusive OR. X XOR x dash always gives you 1, again for the same reason. Now we're focusing to the second and the third row from the truth table. And finally, x XOR y dash gives you the same result as y dash XOR y. And all that together is the same as the negation of x XOR y. So the definition of exclusive OR is quite easy to grasp, and XOR overall is a very useful logic operator. So again, remember that XOR is defined as we have it over here. What is important to note is that the XOR operator is both associative and commutative. Now, based on what we have also defined in previous lectures, that means that x XOR y equals y XOR x, so it's associative, and x XOR y and all of that XOR z gives you exactly the same result as x XOR whatever is the result of y XOR z, so it's commutative. And this is the XOR symbol. Well, it does indeed resemble the OR gate, but notice that we've got an extra line here. Now, this is equivalent if you would like to implement it using only AND and OR gates. This is equivalent to what you see over here. Now, take a moment to look at it. Yes, in case you thought of it, indeed, what we do here is exactly what we give you with the minimized function definition of XOR. You need both x and x dash. You use x and y dash. Then you also use x dash and y. And both of them, you use an OR gate. You pass them as an input, and then you got the XOR. There's also something else, the XNOR, which is the complement of the XOR gate. And XNOR, as we said, being the complement, it's defined as we see over here. It's x XOR y dash, and this is the gate that we use as a symbol. So essentially, it's the same as the XOR gate plus the dot that you see over here at the end, which is used for the complement definition. Now let us provide a very simple example of an operation of XOR. And this is encryption. Now, Encryption is not my specialty, and we're not going to teach you encryption here, but it's going to be very obvious, even to a beginner, why the XOR gate is, the XOR operator is so important. Suppose that you have a 4-bit word that you would like to transmit and you would like to encrypt it. So this 4-bit word has bit B0, B1, B2, and B3. Now suppose that we use, okay, let's call P0, P1, P2, and P3 something like a key. Okay, it's again a 4-bit key. We don't care if we are rigorous with the definition, but this is what we do. We pass for B0, P0 to XOR gate. The result is E0. And we do exactly the same thing for B1, B2, and B3 using P1, P2, and P3 respectively. So you could say that E0, E1, E2, and E3 is now the encrypted version of the 4-bit word we would like to transmit. Now remember that, as we said, X XOR X is essentially 0. So if you pass E0 and P0 as inputs again from XOR gate, then of course this is equal to B0 XOR P0 and again XOR P0. So P0 XOR P0, as we said earlier, gives you a 0. And as we also said, B0 XOR 0 gives you B0 again. Now this is very important because, going back one step, you've seen that by using an exclusive OR logic operator, you can encrypt a bit, and then by using exactly the same encryption bit, you can decrypt it back to its original state. And of course, we do that for each and every encrypted bit, which allows us to get the unencrypted version of the original word which we encrypted and sent to another site. Now let us proceed to another example of using the XOR operator. We're going to talk about something which is called a parity bit. A parity bit is a bit which acts as a check on a set of binary values. So here, in this example, we suppose we got 3 binary values, X, Y, and Z. And we're also going to produce P, which is the parity bit. Now, the parity bit is the XOR operation between all those bits in the set here. And it is calculated, in general, the parity bit is calculated in such a way so that the number of ones in the set over here, X, Y, Z, plus the parity bit, it's always even. Therefore, what happens is that you can use the parity bit as the simplest form of checking whether the transmission of X, Z, and Y on the other side was not erroneous. Now let's see how this works. In this table that you got over here, we got all the possible combinations of X, Y, and Z. Now, by applying the XOR operation, we're going to produce the parity bit for all these possible sets here. This is a result of X XOR Y, and now we're going to XOR this result with Z. So, for the first set of X, Y, and Z values, which is 0, 0, 0, the parity bit is 0. Therefore, the number of ones in the set of X, Y, Z, and the parity bit is even and equal to 0. There are no ones. Now let's see what happens for the second row. For the second row, the parity bit is 1. This means that you overall have 2 ones, which means that you got an even number of ones in the set of X, Y, Z plus the parity bit. And the same thing applies to all the rows here. The parity bit is 1 if and only if it makes the number of ones transmitted on the other side equal to an even number. You can otherwise state this as the 3 parity bit generator that you have here is true if and only if the number of ones in the input is odd. So just let us use one example. This row over here, it has an odd number of ones, y over here. Therefore, the parity bit is 1. Once again, what we do with this operation is that we convert a 3-bit word to a 4-bit word plus the parity bit, which means that you transmit it on the other side, and the other side can tell whether or not there was an error. If the set of bits transmitted to the other side has a number of ones which is not an even number, then you are sure that there was an error in the transmission. Now note one thing: if the number of ones transmitted on the other side is indeed an even number, this does not guarantee that there was no error. However, the only thing that you can be sure about is that if the number of bits transmitted on the other side is not even, then surely there was at least one error. What is interesting is seeing how it works on the receiver side. So on the receiver side, you receive X, Y, Z, and P, and again, you use XOR gates. So you pass them as couples of input bits to XOR gates, and then if needed, you use extra XOR gates to group them together, and the final result is C. You can call this the checker. Therefore, C is essentially the XOR operation applied on all the inputs sent on the other side. And this is how it looks on the receiver side. These are all the combinations of the 4 bits received on the receiver side, and this is the parity error check output, C. Now, the way that this is constructed results in 1 only if the number of ones received is odd, in which case this means that if C is equal to true, then there was surely an error in the transmission. So overall, you've seen that you can use the XOR operator both for creating a parity bit and then for checking whether the transmission was correct or whether there was an error. Again, by using only exclusive logic OR operators. So the possible errors that can be received on the other side are marked here with a red highlight. Everything else implies that the bit stream received on the other side might have been correct. As always, if you have one error happening, then you can detect it with the parity error check. If you have 2 errors, then you cannot be sure, because again, the number of bits received is even, so the parity error check can actually mislead you in this case. But there is one thing for sure: if the parity bit error is equal to 1, the parity bit error check is equal to 1, then for sure there was an error in the transmission. Now let us revisit the addition of binary numbers. As you know, the process is quite the same as adding decimal numbers. What you need to remember is that if you add 0 and 0, you get a 0. 0 plus 1 or 1 plus 0 gives you 1. And if you have 1 plus 1, then the result is 0 plus a carry that you need to carry to the next column. And this is a simple example just to remind you what happens. 1 plus 1 gives you 0 plus a carry over here, which you added to 1 over here. And again, it gives you a 0 plus 1 that you carry next. 1 plus 1 gives you 0, which you carry next. Now, in this particular case, 1 plus 1 gives you 0, plus 1 gives you 1 here. And of course, you got a carry over here. So adding 13 plus 11 gives you 24, and this is the binary format. Now, let's actually remind ourselves how this is done by using another. If you add x and y, and you got the result coming out from here, you need to consider a possible carry coming in and a possible carry coming out for the next column if needed. Now, this is a table that summarizes everything that can happen. If you got 0 plus 0 and there is no carry, this is the result that you get, and this is what you carry out. While here, for example, if you get 0 plus 0 and there is a carry, the result is 1. Take a moment to read this table and remind yourselves what is happening. Perhaps the most interesting case is the last one over here, that you add 1 plus 1, there is a carry, so the result is 1, and there is a carry out. And of course, this case over here, that you add 1 plus 0, or 0 plus 1, and you also have a carry, in which case the result is 0, but you carry out 1. And this is how the addition would work, by chaining together the others. At the end, there will be an out-of-range indicator, which indicates that you need to carry out 1 bit at the end, but we suppose here that there is not enough memory for extracting that 1. So in this case, as you know, we got a buffer overflow. Now let us define what a half adder is. A half adder is a logic circuit that adds 2 bits and provides 2 outputs, the sum and the carry. And this is the table that shows what happens with a half adder. Now, how would you implement this half adder? You would need 2 AND gates at the first level, plus a third one over here for the carry out. And of course, you would need an OR here for the result of the previous 2 AND gates. Now, take a moment to notice how this works. While it is obvious that an AND gate is needed here for the carry out, in case both x and y are equal to 1, you can see that x dash and y on the one hand, and x and y dash, both of them passed through an OR, is actually a XOR gate. Therefore, this circuit over here can be simplified, in a sense, by being rewritten in this way. Now, in this case, you only use 1 level. The circuit has 1 level instead of 2, and it only uses 2 gates. It uses a XOR gate for the sum and an AND gate for the carry out. And this is how you would implement a half adder. But of course, we are not done yet. We need a full adder. Now, what is a full adder? A full adder is a circuit that takes into consideration, apart from x and y, the carry in from a previous full adder. To be more rigorous, the definition is here. A full adder is a logic circuit that adds 2 bits and the carry in from a previous operation and provides 2 outputs, the sum and the carry out. So these are the Carnot gates which we're going to use, and this is the table which is going to help us out to fill in these 2 Carnot tables. As you can see, we need 2 Carnot tables, one for minimizing the result of S, which is the sum of x and y plus the carry in, and we need another one for the carry out. So what we do here is that we use this as sort of a truth table, but unlike other truth tables, we have 2 outputs, S and carry out. Now, we're going to skip the details. You already know how to extract the mean terms. So the first mean term for S is mean term 1 on row number 2. This is the first mean term. Then again, this is another mean term because the result is 1. That's the next mean term, and that's the final mean term. We'll do the same thing, of course, for the carryout. Mean term 5, 6, and mean term 7. So having that done, we can, of course, minimize the S function. As you can see, one interesting here for S is that each and every single bit creates a group on its own. Therefore, the minimized S function is what you see over here. It's the sum, the logic sum of all the mean terms that we have in the table. And if you convert this to a circuit, this is how it's going to look like. It's going to be a sum of products, a typical case of a sum of products. You got the first level with the AND gates here, and you got the second level with an OR gate at the end. Now things are a little bit slightly, let's say, more complicated, if you could say, for the case of the carryout. For the case of the carryout, we have 3 groups to identify here, essential ones. It's this group over here, the red one, the green one, and the blue one. So carryout would look like this. And of course, you can easily convert that to a second. Now, what does that exactly mean? While for the case of the carryout, we keep the same circuit, there's nothing more we can do about it. For the case of sum, we can do a series of operations. Now, if this is the definition of the sum, what you can actually do is extract the carry in dash as a common term here from these two. And you can do the same thing for these two terms and extract carry in as a common term. So you can rewrite the sum as this. Now, notice one interesting thing here. This is XOR, isn't it? And based on your experience, this is a dashed XOR. If you don't remember these two, go back to the definitions in the first slides in the beginning of this presentation. So the outcome of all this is that we can use XOR gates for part of the full adder. Now again, if you revisit what we've said in the beginning of this presentation, during the first slides, you can actually convert everything into a series of XORs. So carry in XOR X XOR Y. And of course, this gives you that the part of the full adder which is possible for the sum can be implemented with 2 XOR gates, 2 levels, and only 2 XOR gates. And this is what you need for the carryout. So if you would like to implement an n-bit adder, in other words, an adder that considers n bits in a row, this is how it would look like. For each pair of bits, A and B, you would need a carry in, and you will get a result, which is the sum. For the sum, you would need 2 levels of XOR gates, and for the carryout, you need this part of the circuit. And of course, you would feed the carryout as carry in to the next full adder. Nevertheless, we're not done yet. You may know now how to build an adder, but there are some questions here, some challenges. This is an adder, but for which binary system exactly? What happens in case of an overflow, where the carryout of the last part of the full adder here is 1? And for a natural binary system, in other words, a system that uses unsigned magnitude, what happens for everything else? So let's check out together what happens in the case of 2's complement. Regarding overflows, remember that with 2's complement, having a carry out does not systematically mean that you have an overflow. In fact, remember that with 2's complement, if the most significant bit of a number is 1, this means that it's a negative number. If it's a 0, this means that it's a positive number. And overflows can happen only if you're adding numbers with the same sign. Therefore, if the most significant bit of the first number you're adding and the most significant bit of the second number you're adding, if they're different, then there is definitely no overflow, even if the carryout is 1. Now, if the two most significant bits, the most significant bit from the one number that you're adding and the other number are the same, so if they're both positive or both negative, and at the same time they are different from the last summation result of the last full adder over here, then in this case you have an overflow. So the case of 2's complement is a little bit special. You need to remember this rule, you need to apply this rule when you have a chain of full adders. Having that said, let's see how you would handle this with a circuit. So this is the last full adder, and we're going to focus on the last full adder. This is why the result here is the summation of position n-1. Remember that we always start from position 0 all the way up to position n-1, which is for the most significant bit result. Now let's focus on this table over here. This table is going to tell us whether or not we got an overflow. The two rules that we previously mentioned can be written in Boolean algebra terms like this. Now, in natural language, both of these functions say that if the two most significant bits are the same and at the same time different than s n-1, then you have an overflow. And in the table, this is where you can find that. So you have an overflow only in these two cases. In these two cases, the two most significant bits are the same, either 1, 1 or 0, 0. And at the same time, they are different than s n-1. Regardless of the carry in that comes in, there is definitely an overflow in this case. Now, having that said, we can proceed with defining what an overflow is. So again, we have the same table here. We notice that the min terms are 3 and 4. Therefore, you can write that the overflow function as a sum of products looks like this, which, as you know by now, it can be rewritten using the XOR function. Therefore, if we suppose these two complement 4-bit adder as our example, then each and every full adder in this chain will internally look like this. So this would be the part of the circuit for the carryout, and this would be the part of the circuit for the sum, which is composed by 2 XOR gates, as you know by now. And for the overflow at the end, as you've seen in the previous slide, you just need XOR being applied for carryout 4 and carryout 3. So in this very simple example, you see how in the case of 2's complement, you can easily add two numbers by applying this circuit over here, chaining it together by repeating itself, and by applying just XOR operation at the end between carryout 3 and carryout 4, you can know whether or not there was an overflow. Now let us see by example how you would implement a 2's complement subtractor assuming only 4 bits. To do so, we're going to use an example which is exactly the same as the example we used in slide 12 in lecture 3. Now, as we mentioned there, when you're using 2's complement, negating a number is as simple as inverting all of its bits and adding 1. Therefore, if you're trying to subtract -6 from -3, you can convert that to an addition between this number over here, which is -3, and of course, for this one over here, you just invert all of its bits and you add 1 at the end. Therefore, the result is going to come out of an addition. If you perform this addition, then the result is going to be 0011, which in terms of 2's complement means 3. As for the carryout at the end, as you all know, this is ignored. And in this particular case, it doesn't signify an overflow, which can be verified by the XOR gate here, which is XORing the last carryout and the one before the last. So this means that you are XORing 1 and 1. Let's see that together. If we perform the operation step by step, 1 plus 1 gives you a carryout. Then 0 plus 0 plus 1 does not give you a carryout. Now, this is going to give us, if there is one, carryout 3. 1 plus 1 gives you a carryout. So C3 here is 1. And then 1 plus 0 plus the carryout, it will give you the last carryout. So the last XOR operation over here takes as input 1 and 1, which due to the XOR operation will give you 0 for the overflow. Therefore, you've seen how with this addition over here, we performed the subtraction, which resulted in a negative indication about an overflow, because the carryout at the end here, in this case, it is neglected. Now, in order to show how we would do the initial steps that we referred to by negating all the bits and by adding an, this is as simple as negating all the bits that are passed in the adder here, in each and every adder. And in order to add 1, you just pass it as an input here as the first carry in to the first full adder. So by negating all the bits of the second number here, and by adding 1, you are essentially managing to convert this number to 2's complement. And in this 2's complement format, it's very easy because you can simply add it to the other binary number, go step by step, and then check if the carryout at the end signifies an overflow by XORing C3 and C4. So let's see how we can make things a little bit easier with respect to converting a number into 2's complement so that we can just use an addition. The way to do so is by introducing m over here. As you can see, if m is equal to 1 and you pass it through these XOR gates over here, along with the bit inserted from the second number, the result will be an inverted bit. So if m is equal to 1, then you are inverting all the bits of the second number. However, if m is equal to 0, then you're not changing these bits. You're not inverting them. At the same time, you're passing 1 as your first carry in over here. And as we said in the previous slide, by inverting all the bits of the second number and by adding 1, the second number is converted into 2's complement format. Therefore, you can proceed with the addition over here, which covers both the cases of adding 2 numbers or subtracting 2 numbers. What is interesting to note here is that all the bits, in theory, of the 2 numbers can be added in parallel. Nevertheless, that's not entirely true. What happens is that the most significant bit of the sum has to wait for all the other bits to be added. And why is this? Well, because it needs C3 here. Therefore, C1 propagates through 3 full adders, which means overall, as you can see from here, 6 level of gates. 3 adders times 2 level of gates for each adder. This means that you cannot perform the operation in parallel. In other words, this is not fast, especially with sizable n-bit words. What should have been something that can be done in parallel actually is done in series. To overcome this problem, we use something which is called look-ahead carry architecture. Now remember that this is what we previously defined as a half adder. What we can do is put in series 2 half adders in this example over here. This means that the sum Si over here is the result of XORing the bit from the first number and the bit from the second number, and also XORing with the carry in. Now let us see the implications that come out of this. We start from the input carry. The first carry in after the input carry is the result of G0 from the first half adder, or P0 and C0. The same applies for C2. It comes as a result of ORing G1 with P1 times C1. And that gives you this result over here, which means that the next carry, C3 over here, is a function of G0, C0, G1, G2, P0, P1, and P2. And that is a sum of products, just like it was a sum of products for C2 and for C1. In case this is not obvious to you, remember that G0 over here is a product of G0 and 1. Same as G1 over here is the product of G1 and 1. So all of the carries, by applying this architecture, are a sum of product. This means that all the carries can actually be calculated by looking ahead. And as you know, a sum of products from the previous lectures implies 2 levels. So for carry 3 over here, which is needed for adding the most significant bits here, you only need 2 steps as a sum of products, so that you can compute S3. Again, the addition is not done in parallel, but the number of steps needed for computing C3 here is only 2. And therefore, the look-ahead carry architecture is much faster than the architecture we've shown in the previous slide. And as we said in the previous slide, if you put everything together, it becomes obvious that the main advantage is that you use only 2 levels. A level for the AND gates, in other words for the products, and a final level for the sums. So the final slide for today addresses the problem of how to build an 8-bit adder. Now, if you're given an MSI carry look-ahead 4-bit adder, you can simply use 2 instances of the same 4-bit look-ahead adder. The only thing you need to make sure is that for the 2 numbers you're trying to add, you will pass the least significant bits through the same MSI carry look-ahead 4-bit adder and the most significant bits from the second one. And for the red number, you pass again the least significant bits through the first MSI carry look-ahead 4-bit adder and the most significant bits for the second one. And this is how you can build an 8-bit adder. Obviously, for a 12-bit adder or for a 16-bit adder, you need just to add an extra series of MSI carry look ahead 4-bit adders. And the operations, of course, take place in parallel.